right, we're now recording. Let me hit just a few kind of minor announcements, I think, but things you might be interested in. Tomorrow on the Birmingham East Campus in the A.G. Gaston building, you know about the taming of the... You wanting to go, that's what you were saying, right? Yeah, the taming of the shrew. It should be fun. It's UAB company, right? Okay. So it should be a lot of fun. Shakespeare was brilliant, and he had one of the best grasp, of the English language of anyone. Boy, he could play puns like nobody's business. And so his language is always exciting, funny, and it's a comedy for sure. So it should be a lot of fun. I might be required to go too. It depends on the crowd. I'm going over there, and if it's a good representation, then I'll.
Supposedly, the dean canceled our Friday class, saying it's mandatory to go.
Oh, okay. Yeah.
For a test,
right.
To make up the class. I was like, okay.
What class is this?
Had biology 102.
Really?
Yeah. She told us too. She's like, Friday is canceled because the dean told me you have to go to this. It's mandatory. Like she said, I was like, oh god.
Well, then there's probably going to be enough people there. I hope there's enough seats. That's.
But our class is short. It's like 12 people.
Huh? Yeah.
Our class is short.
Well, the thing is, I can see maybe humanities and English and literature, those kind of things. Yeah, that fits like a glove. Biology?
Yeah.
I don't think there's a lot of biology in taming of the shrew, I don't think they're going to dissect the shrew, so that's not going to happen. Yeah, but it really is. But that, to me, I think I'm going to disagree with that. But I'll go over there just to make sure that there aren't seats left open. So, all right. So you know about that. Okay. Number two. I don't know if y'all realize that I've been having a terrible automotive week. Okay. And right now my car is at Pet Boys, but it's not running. I'm in a rental car. That's why I had to go down to see if I could get a temporary parking pass for the rental car. But the police aren't in the office. They weren't in when I came in this morning. They weren't in between these two classes. And actually the woman down there said she doesn't know if anyone's in there because Lieutenant Tate, who's usually in the office, is having surgery. So maybe everybody else is out patrolling. Hopefully they're not giving me tickets, because I called them and said, look, I can't get a temporary. Would you refrain from ticketing me until I can get one? And they said, oh yeah, no problem. So I hope that word got around. Okay, so anyway, during my office hours this afternoon, which are 1:15 to 3:15, hopefully I won't have to leave campus, but I've got to deal with a whole bunch of things with the insurance company, with getting my vehicle towed, all sorts of mess like that. I think I can do it all from my office, so I should be in there. I'll stop what I'm doing if you have any questions or need me. But if I do have to leave campus, like if they're going to come to it, then I have to get over there and get my stuff out of it and stuff like that. But I don't think that's going to happen now. Hopefully I can wait until, well, they're going to be closed by the time I get off of work today. So I may have to go over there and get my stuff out of it during the office. No, actually, they may be open past 8, so I might be able to get it after work. So, anyway, I don't know of any others right now, so we'll go from there. Okay. Let me also say this. I'm probably preaching to the choir here. This class is probably one of my best classes as far as getting research papers in. I've already got 1, 2, 3, 4, 5, 6, 7 in out of, 16 students or something like that. So that's not half, but it's doing pretty well. Your first test, all but 2 people have turned that in. And of course, those 2 people are not here. So, no, wait, one of them is here. Okay. So please get your first test in. Okay. Second test, y'all still have, so get those as soon as you can. We just got started on chapter 5, so you got some time for that one. All right. Let's move on. Any questions, anything we've done so far? And let's go to current slide, and here it is. No questions so far? Okay. We're on page 357. This is chapter 5, Analytic Trigonometry, section 5.2, Verifying Trigonometric Identities. We sort of started on this a little bit at the end of 5.1. We're really going to get into it in this section, and then we'll continue some other things in the next few sections. Verifying trigonometric identities is a useful process when you need to convert a trigonometric expression into a form that's more useful algebraically. Now, some of these trig expressions can get really big and hairy, and sometimes you like to simplify them. When you verify an identity, you cannot assume that the two sides are really equal. That's what you're trying to show. So therefore, when I do it, I always put a question mark over the equal sign, page 357, okay? I put a question mark over that, reminding myself I don't know that they're equal. As a result, when verifying the identities, you cannot use operations such as adding the same quantity to both each side, because then you're changing those sides. So again, do not cross the equal sign. You can operate on this side, you can operate on this side, but narrow the twain to meet. Now, you can look across the equal sign and say, yeah, I need to get it in that form, well, we'll get it that way. But you can't cross it, okay? It reminds me of two of my nieces when they were young. They fought like cats and dogs, okay? All the time. And my brother and his wife finally, when they were going on long trips, and they were always kicking at each other and doing this in the back seat, my brother finally put the cooler in between them, and everything piled them up so they could hardly talk with each other back there, you know. And I can remember this one time they were driving from Georgia or Louisiana or somewhere, and were going to stop by and see us on the way. And my brother was so frustrated by the time we got here, he said, yeah, he had them completely separated. They couldn't touch each other. They couldn't pinch each other. They couldn't be on each other's side. And then one of them said, she's looking out of my window. You know, so that's allowed. You can look across the equal sign, but you can't cross it. Okay. So don't use adding things both sides, cross multiplication. Do none of that. Keep separate what you do on the two sides. Except you can look across and see what you're trying to get for. All right, so here's one to let's do. All right, you tell me what you think a good first step would be to verify that identity. And remember, there's no definite steps, there's just sort of general rules. What would be one thing you might think of doing?
Sine squared theta is 1 minus cosine theta.
Say that again.
I said sine squared theta is 1 minus cosine squared theta.
Okay. Is that necessarily going to help you get to something that looks like on the left-hand side? What you said is absolutely true, and you can try it. But here's one thing. This is the first thing we said. One of the first things. Usually start with the more complicated side and see if you can get it to simplify to look something like the other side. Now, it's just because I've been doing these an awful long time, but one thing I'm going to say now, let's see if using just some simple algebraic stuff will work before we get into trigonometric stuff. For instance, there you have like a squared minus 1, or a minus 1 over b, okay? Actually, it's a minus 1 over a. You can split that off into two fractions, right? Same denominator. What would that give you? Okay, wait. Here, okay. Now, the book is going to go a different way, and their way is perfectly fine too, but this to me looks like a good thing to do. Secant squared theta over secant squared theta minus 1 over secant squared theta. Now, like I said, I put a question mark over that. Is that the same as sine squared theta? We don't know yet. But what is secant squared theta over secant squared theta? 1 minus. And what is 1 over secant squared theta? Cosine squared theta. And there you had exactly what you were saying, right? And we know those are indeed true. Yes, that is sine squared theta by your Pythagorean identity. So that's one way to do it. Not always will they, in fact, most of the time they won't be that, I don't want to say obvious or easy, but they won't be in forms that you can easily do that. But this one, hey, you can split that into 2 different fractions. Those fractions simplify very nicely to be an identity that you know, okay? The book, though, is going to take another bent, and that's fine, too. And one of my the book's last resort, one that I like to do, normally my rule is, if you see squares, that's different from seeing stars. No, I'm kidding. If you see squares, then think of Pythagorean identity. And secant squared theta minus 1 is secant squared theta minus 1 is? And which is it? What is that equal to? Tangent squared theta. Okay? So you could have tangent squared theta over secant squared theta. That was actually the first thing that came to my mind, because that was obviously that. And then what I would do was get both of those in terms of sines and cosines. That's my favorite thing to do. Once you got that, then, so this would be tangent squared theta over secant squared theta. And frankly, I think I'd rather write this as tangent squared theta divided by secant squared theta. Okay, tangent squared theta is what? From ratio identity. Sine squared theta over cosine squared theta. And secant squared theta is what? 1 over cosine, but then if you change the division to a multiplication, right, that would be times cosine squared theta over 1. And there, and with sound effects, you have sine squared theta. Okay, I skipped a step.
No. I'm just like, so sine squared theta is tangent squared theta divided by secant squared theta?
Let's see if that's true. It may be another identity. You said sine squared theta is
Tangent squared theta over secant squared theta?
yeah, that's what we just did.
Yeah, I know. That's why I was just asking how you.
Yeah. But you see, that's not an identity I know. I know these. Tangent squared is sine squared over cosine. Secant squared is 1 over cosine squared. I should have squares everywhere. But when you divide, you invert and multiply. So that makes cosine squared theta over 1. Multiply, those cancel out. And sure enough, tangent squared theta over secant squared theta is indeed sine squared theta. Just like secant squared theta minus 1 over secant squared theta is sine squared theta. That's not one to. Yeah. Yeah, I think it's a little easier that first way, but both ways are fine. And if I'm not mistaken, the book does it the second way I did. So let's erase all this and see how the book did it. But the point of all this is there's many ways to get there, okay? And I never would have done it this way, okay? Yeah. I would have recognized that secant squared theta minus 1 is tangent squared theta. They said, well, secant squared theta is tangent squared theta plus 1, and then subtract 1 from that, and the 1's go out, and that's how they get tangent squared theta over secant squared theta. Okay, that way you can do it too. It's a different Pythagorean identity, but it's fine. So that gives you tangent squared theta over secant squared theta. So let's see what they come up with next. I think they keep it vertical. They don't do horizontal like I did. Nope. What they did is tangent squared theta times 1 over secant squared theta, and that is tangent squared theta times cosine squared theta. It's true. It's not as obvious to me, but yeah, it's absolutely true. And then rewrite tangent squared theta as sine squared theta over cosine squared theta. Then they go out. Same way we did it, okay? And that leaves you sine squared theta. So sine squared theta equals sine squared theta. Notice we never crossed the equal sign, but we kept our eyes on what we're, the prize, that we're going for. Now, my general rule then is, once you have it in sines and cosines, don't go messing with it. Okay, keep it simple. Okay. The things not in that, yeah, mess with those. Notice that you verify the identity by starting with the left-hand side, the more complicated side, using those fundamental trigonometric identities. I used algebra first and then used the trig identities to obtain what you want on the right side. All legal steps are allowed, okay? Just don't do anything illegal and you're fine. But if it's true algebraically, you can do it. If it's true trigonometrically, you can use it, okay? So that was example 1, top of page 358. Now, every one of these examples is followed by a checkpoint. A good idea to go home or go to the library, go to another classroom, go somewhere and try to do these as soon as you can after class so you can verify that indeed, do it while it's fresh on your mind, okay? Now, can you believe it? That's the only thing they do in this section. All those lead-on slides and one example. So what I'm going to do is do the rest of the examples, okay? So let's do example 2. Example 2 says to verify this. 2 secant squared theta, alpha, sorry. Oh, no! I just erased. I went to do an eraser and I erased everything, so sorry about that. All right, let's start over. 2 secant. I can't write. Okay. 2 secant squared alpha is equal to, or supposedly is equal to, 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. Okay? What would you suggest we do on a problem like this? Okay, I like that idea. The book is going to say, go with the more complicated side, but I say, let's do both sides. This one, let's get it in terms of cosine. Sine and cosine, and that would be what? 2 over cosine squared alpha, right? So secant is 1 over cosine squared. Secant squared is 1 over cosine squared. So there we got the left-hand side as simple as I can think of it doing it right now, okay? Now, what can we do to the right-hand side? And we still don't know if these are equal, so I like to keep my question mark there. Okay, in other words, get at least common denominator, which is going to multiply the first term by the second term's denominator, and the second term by the first term's denominator. Don't cross the equal sign. So you're going to have to multiply this by 1 plus sine alpha, and multiply this one by 1 minus sine alpha. But you can't just multiply the denominators. You're multiplying by what? 1. And what is the form of 1 that you would do? Multiply the denominator by 1 plus sine alpha. What are you multiplying the numerator by? 1 plus sine alpha, because that's equal to 1. And over here, you're multiplying by 1 minus sine alpha, okay? All right. So now that you got the same denominators, in most of the time I'll leave it in factored form. This time I say not, okay? You only multiply those denominators out, and what does that give you? Okay? Your common denominator is 1 minus sine alpha times 1 plus sine alpha, right? If you multiply those together, what does that give you?
1 minus
Oh, that sounds like a good thing to have, isn't it? 1 minus sine squared alpha. Okay? That's your denominator. Your numerators are what? 1 plus, you got same denominator, so you add your numerators. That's how you add fractions. Keep the denominator, which we did. 1 plus sine alpha plus 1 minus sine alpha, right? You just add your numerators together. And what does that give you? Okay, the sine alpha minus sine alpha is 0. So that gives us a 2. And what is 1 minus sine squared alpha? Cosine squared alpha. So you got the same thing on both sides. Okay? So that's why I find the advantage of simplifying both sides. Just don't cross. You can look across and see if it's going where you want it to go, but don't cross the equal sign. Simplify this side, simplify that side. If you get it to the same simple form, yes, you're happy camper, right? And if you notice how they did it, they only worked with the right-hand side, and when they got down here, they said this is 2 times secant squared, which took them an extra step to do it. Since you were doing it as you went, you got that extra step already done. Okay. Again, there's a checkpoint. I highly recommend you try those. Okay? Now, they are coming up with some things. They act like they're brand new, and they're not. But at the top of page 359, they have 3 Pythagorean identities as if those are the only 3. Sine squared u plus cosine squared u is equal to 1. Yeah, we know that. But that set leads to 2 more, and we had already done this. I do it every time I teach the identities. And then that's the same as saying sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. Yeah, that's not new. And 1 plus tangent squared is equal to secant squared. That's the same as 1 is equal to secant squared u minus tangent squared u, or tangent squared u is equal to secant squared u minus 1, which we used in the previous one. And 1 plus cotangent squared u is cosecant squared u, and just like above, that would be 1 is equal to cosecant squared u minus cotangent squared u, and cotangent squared u is cosecant squared u minus 1. Just different ways of expressing the same identity. So there's nothing too new there. All right, ready for example 3. Okay. Verify this identity. They did the very simplest one and then skipped all the rest of them as they got harder and harder. Okay. Here we'll start with tangent squared x plus 1. For some reason this is not writing well. Times cosine squared x minus 1. And the question is that equal to minus tangent squared x? Okay? What's that? I can't hear.
I don't think they're equal.
You don't. Okay, so they don't. They're throwing a curveball at us, aren't they? Okay. Well, what is this? Okay. What would be your approach to approaching it, to solving this?
Trying to get them in terms of, well, not sine, cosine, but I'll just tell you how I did it.
Okay. How would you start?
I changed the tangent to secant squared.
Okay, change that. That is exactly your Pythagorean identity of secant squared theta. Secant squared x, right? That's exactly. So, yeah, if I could use a Pythagorean identity to simplify, yeah, I think I'll do it. Okay? And then what does this become? Not quite. 1 minus cosine squared is sine squared. So this will be minus sine squared. Okay. So maybe they got it right after all, huh? Okay. Now, I think I like to work on both sides. I do want to get that tangent squared into sine squareds and sines and cosines. So what would that be? Sine squared x over cosine squared x. Okay. Ah, yeah, secant squared is exactly 1 over cosine squared. And this is a minus times a minus sine squared. And it doesn't take any imagination at all to see those are exactly equal. Just multiply numerator together, you got that. Denominator together, you got that. That is exactly equal to minus sine squared theta tan squared x over cosine squared x. Exactly, right? So, did turn out being negative sign, okay. So you were close but no cigars. Okay, how about example 4? I find these are sort of fun. What's that? I can't hear you.
I said they're fun until they're not.
Well, when I was a little kid, I always loved solving puzzles. And I think that's why I like them, because I treat them like a puzzle. So, and there's checkpoints after every one, remember? Here's another one. Verify this. Tangent x plus cotangent x what's that? I can't hear.
Are you doing B first? In my book, they have an A part and a B part.
Okay. And which one? Example 4 or 3?
In example 4.
Okay. All I see in mine is just one. Have you got the new text or the old text? Okay. I've got the new one here, but those people who had been here, they had the old. So let's see. This is 5.2. So I think we must have found. Oh, I see. Okay, so yeah, this was the B part. So I'll do the A part also. But since I got this one halfway written down, I'll do it. And since I got Tyrell halfway here, I'll mark him. Okay. All right. Whopping big class today. Are people already getting fired up about the Magic City Classic? Is that what's going on? You think so? Okay. Well, one of the other adjunct instructors said, yeah, I'm not expecting many people. This was last night. That was Magic City Classic. I thought, already? Isn't that Saturday? But I guess there's activities going on.
Yeah, I know a lot of people come out there and still.
They're already there, huh? Okay. Well, not me. I like sleeping in my own bed. Okay. All right, let's do the B part first, then we'll go back and do the A part. Sorry, I didn't realize that. The B part says tangent x plus cotangent x, is that equal to secant x cosecant x? What'd you say?
I say you gotta get it in terms of sine and cosine.
Okay, I'm all with you there. If any of these had squares in them, then I'd look and see about Pythagorean identities. They don't. So let's get them all in terms of sines and cosines. What is tangent in terms of sines and cosines? Sine x over cosine x. Plus, and what's cotangent x? Cosine x over sine x. Now, is that equal to, and what is secant x? 1 over cosine x. And what's cosecant x? 1 over sine x. Okay? Now, what do we need to do to the left-hand side? Left. Oh, I see. Yeah. Okay, go ahead. You need addition or subtraction of fractions, so you need a common denominator. What would that common denominator do? They get a b? It would be the product. We multiply the two together. So what we would have to do is multiply cosine x by sine x to get that to be the same, but that means multiply the numerator by sine x as well. And multiply the second part, the denominator, by cosine x, which you're required to multiply the numerator by cosine x as well. So that winds up with a sine squared. Okay, now you have common denominator, so you can add them together, add your numerators, and what does that give you? Sine squared x plus cosine squared x over that common denominator, sine x cosine x, or whichever order you want to do them. But what is sine squared x plus cosine squared x? 1. So this is simply 1, and this is simply 1 over sine x cosine x. It doesn't matter which order you write them, if it will write. Okay. So yes, indeed, they are the same. All right, so that's the B part in the new book. Those of you who have the older edition, which I thought probably most of you would have, let's do the A part. No, that was your only part. For those of the newer edition, let's do the A part. Any question on that before I delete it? You see the steps? Okay. Okay. In the new text, the A part of example 4. Tangent x times cosecant x supposedly they claim is equal to secant x. We don't know that for sure, but let's see. What would you do here? I like the idea. So what is tangent x in terms of sines and cosine? Sine x over cosine x. And what's cosecant x in terms of sine? 1 over sine x. Okay, excuse me. Excuse me. Excuse me. Okay. And what is secant x in terms of sine and cosine? 1 over cosine x. Okay? And what do we notice here? Sines can divide away, and you've got exactly 1 over cosine x equal 1 over cosine x. Done. What do they say? QED. Okay. And see, you could have left that as secant x on the right, but then you would have had to change this to. So it's just simple to me. It's simple to go. Pay as you go. Okay. So if there are any others that come out that way, let me know and I'll do all those. Okay, that was example 4. How about example 5? Any questions on this before I go to it? Okay. All right, verify this one. Secant x plus tangent x, is that equal to, could it be equal to cosine x over 1 minus sine x? Okay. Now, what would be your approach here? I like that idea. I'm going to hold in abeyance a tendency to want to do something to the right-hand side. It's already in sines and cosines. If I need to, I got a couple ideas there. But let's see what happens when we just get the others in terms of that. What is secant x in terms of sine and cosine? 1 over cosine x. And what's tangent x in terms of sine and cosine? Sine x over cosine x. Okay? Well, you got same denominator, it's cosine x, and what's your new numerator? 1 plus sine x. Okay? Is that the same as cosine x over 1 minus sine x? It sure doesn't look like it. Now, there is a tendency for me to say, hey, those are two ratios equal to each other, let's cross multiply, but you're not supposed to cross the equal sign. So we're not going to do that. Okay? So here's what I suggest. If you get to an impasse like this, and you have something that is I think I mentioned this before, but this form and this form could be expressed as conjugates. So multiply by conjugate. It doesn't matter which one you do. Let's just do that one. Okay? So let's multiply this one by, what is its conjugate? 1 plus sine x. And if we multiply the denominator over that, we got to multiply the numerator by that as well. So it looks like we've just made it a lot more complicated. It sure doesn't look like we've simplified it any, right? Well, let's see. We're just going to mess with the right-hand side for a while now. Let's leave that in factored form and multiply the denominator out, though. What does that become? Numerator we're going to leave alone. Okay, what did you say it was? 1 minus sine squared x. Well, what is 1 minus sine squared x? That's cosine squared x. So you have a cosine x times 1 plus sine x over cosine squared x. Well, one of these in the denominator is going to wipe out that one in the numerator, right? I did too much there. Okay, so that leaves us with, guess what? 1 plus sine x over cosine x. 1 plus sine x over cosine x. Same thing. So sure enough, we've got the same, those are the same identities. Even though we looked across there to see what we might get, we stayed on our fair side. We didn't cross the equal sign, and sure enough, we got the same thing. You verified that with that. Make sense? So whenever you have a situation that don't see where else to go, that's a trick. Okay? Multiply by conjugate. See if that helps you. And you see, especially if it's something like this, multiplying its conjugate is going to give you a Pythagorean identity. And that's usually pretty helpful. When I was an undergraduate at Georgia Tech many decades ago, I was very fortunate to have the same professor for all, we were on the quarter system, all 5 quarters of calculus, okay? And he was really good. He was really, really hard, but he explained things so well. I never understood what he was doing until usually at the end of the term when I look back over all my notes and say, oh, this makes sense, you know. Along the way, I was just trying like everything to keep up with what he was doing and had no clue of why he was doing it or anything else. But then when I look back, I say, oh, look at this. Yeah, this is making sense, you know. Not always, but that's how my first quarter anyway was. Well, we finished everything we needed in that 5th quarter of calculus because we had him for the same instructor. We get a little bit ahead, and soon he said, well, you know, we pretty much finished everything that's required for the course, and we had maybe a week left, and we met 5 days a week. You know, we met for 50 minutes a day, 5 days a week. 10 o'clock, okay, Monday through Friday. And he said, let me go and sort of get you ready for differential equations. I know you're all going to take that next. So he started introducing us to differential equations. And I remember he said this. He said, a lot of times differential equations, often differential equations, comes down to, well, let's try a trick here. He said, and if the trick works more than once, call it a method. Well, that's the thing here. If you can't get anywhere else, but you have something that's a 1 plus or a 1 minus something, the trick is multiply by its conjugate to see if that helps you. If it does, it becomes a method. Okay? If it doesn't, try another trick. So that's what we're doing sometimes, is trying tricks, and if they work, we'll call them a method. Okay? And that worked this time. Okay. Let's go to a new one. Any questions on that before we move on? Okay. That will get us up to example 6. Verify this identity. Cotangent squared theta, they love changing their variables around, don't they? Plus, over 1 plus cosecant theta. Is that equal to 1 minus sine theta over sine theta? Okay. Now, finally, the book says, okay, now you can work each side separately. We've been doing it all along, almost all along. Okay. What would be your first thought? Okay, or is it cosecant squared theta minus 1? Which is it, that one? Okay. Yeah. All right. Here is I can find you. Jeremy. Yeah. All right. First suggestion here, we're on example 6 in chapter 5, analytic trigonometry, section 5.2, verifying trigonometric identities. This is example 6, verifying this trigonometric identity. And Ilse's first suggestion was, here we see a square there, so why not get it in terms of its Pythagorean identity, which will be cosecant squared theta minus 1. Agreed? Over out. Here's something I'm going to do you don't have to do, but I'm going to do it now. Because this is an addition, it doesn't matter what order we add. Subtractions matter, but the additions don't, right? They're commutative. And since you have cosecant first here, I'm going to flip this around and make it cosecant plus 1. It's the same value, right? So this is going to be, you don't have to do this, I'm just choosing to do it. Cosecant theta, okay? Plus 1, okay. I'm going to leave the right hand side alone for a while now. Okay. Did you have a question? Oh, okay. Now, that might hint to you what I'm going to suggest doing next. What is this now? A difference of 2 perfect squares, exactly. So we can, what's the F word? Factor it, okay. Yeah, in this class, factor is the F word, okay? So that's going to be, how does that factor? Cosecant theta plus 1 times cosecant theta minus 1 over cosecant theta plus 1. Hey, and guess what we can do? Divide that out. But now the question is that equal to 1 minus sine theta over sine theta? It doesn't look very likely, does it? So what might we try next? Say that.
I was saying break up the fraction on the other side.
Okay, now that's not a bad idea. Okay, and Doc is here. Okay, so on this side, you're just going to algebraically separate this and make it 1 over sine theta minus sine theta over sine theta, right? Whoops. And what is sine theta over sine theta? 1, okay. So this is going to be a 1, okay? Now, one thing left I think I would do here. One of our favorite things to do. To sine or cosine, and that would be sine. What would that be then? 1 over sine theta minus 1. And what do we have over here? 1 over sine theta minus 1. Yes! Same thing on both sides. We got it. And again, there's many ways to do these. You don't have to do it this way. As long as all your steps are legal in most states, then you can do them. Okay? Just don't do any wrong steps, because you'll screw yourself up. As long as all the steps. And you can look at the way the book did, and they probably do something different from that. But, yeah, they get the same place, verifying that they're the same. And again, there's checkpoints after every one. Now, what's the advantage of a checkpoint, doing a checkpoint? Yeah, if you get stuck, you can go to larsonprecalculus.com and see an audio-video solution to every checkpoint, okay? So as soon after we finish class, if you can, get out there and see if you can work those. If you can't, pull up the video, okay? All right, so that was example 6. Example 7 has 2 parts, and they say examples from calculus. Okay. And they actually turn out to be 2 of the simplest ones, I think. Okay? Verify each identity. Here's the first one. Tangent fourth x. Their claim is that's tangent squared x. I can't write. Times secant squared x minus tangent squared x. All right. What would you suggest doing first? Okay, you certainly can, but remember, if there's some simple algebraic things to do, you don't want to do those. Is there something algebraic you can do on either side there? Second? Okay, that's not a simple algebraic thing. Canceling out is never a lot. No, I mean, canceling is dividing out. Okay, what do you mean by dividing if you say cancel? What I would say, what's the F word? Factor out. What were you suggesting? Tangent or tangent squared? Tangent squared. I agree with that one finally when I got you to say it. Okay. Now, is that equal to, let's factor out a tangent squared. Okay, and what does that leave us with? A secant squared theta from the first term, or x from the first term, minus 1 from the second term. Oh! Okay. Chelsea's here. Okay. Slowly we're getting a good sized class. And then what is secant squared x minus 1? That's tangent squared x, and tangent squared x times tangent squared x, sure enough, is tangent fourth x. Okay. So I don't usually say it this way, but if there's something simple algebraically you can do, then try that first and see if it makes anything easier or obvious. And usually when you have the squares, see if you can use Pythagorean identities, okay? And then when all else, not when all else fails, but if neither of those works, try getting in terms of sines and cosines. So what you said would certainly work, but it's going to have lots of terms and lots of things in it. Like I say, they will work. Okay. And it might not be any harder either. That was the A part there. You want to try the B part? I think we have room even to do it right here. Cosecant fourth x times cotangent x, is that equal to cosecant squared x times, they've already factored this one for you, cotangent x plus cotangent cubed x. Now, for the life of me, I can't remember ever using that in calculus. Okay, I think I might have an idea where you might, but it's a stretch. What might you try to do? Any ideas? Think of something. Come up with something. Any idea worthwhile? Say again? Factor that on the left side or right side? That right side? Okay. Yeah. You can factor a cotangent out of that parenthetical expression, can't you? So and that's especially attractive because you have a cotangent by itself over here. So you can look across the window, you can look out the other window if you want to. Okay? So this, we still don't know if it's equal, be cosecant squared x times cotangent x times, and what's left there if you factor out a cotangent? 1 plus cotangent squared x. What's that? All right, there we have it again. What is that? 1 plus cotangent squared x is? Cosecant squared x. And so cosecant squared x times cotangent x times cosecant squared x is indeed equal to, and Whitney's here. And you're sitting in her seat. No, okay. Is Justin not coming? Or yes. All right. And sure enough, when you multiply cosecant squared times cosecant squared, you get cosecant fourth times cotangent x. Yes. Right? All right. Good deal. And there's checkpoints. Okay. This was example 7, A and B, on page 361 in section 5.2, verifying trigonometric identities in chapter 5, which is analytic trigonometry. And believe it or not, we just finished 5.2. Almost. Okay? Say again? Do you have this yet, or do you need it a little longer? Or do you need any explanation? You okay? Okay. All right. So let's go back to 5.2 exercises and do the vocabulary. Fill in the blank. An equation that is true for all real values in its domain is called an identity. An equation that is true for only some values in its domain is called a blank blank. Flip back to page
conditional equation.
conditional equation. Exactly. All right. Examples 3 through 8 fill in the blank also to complete the fundamental trigonometric identity. 1 over cotangent u is tangent u. Number 4. Cosine u over sine u is cotangent u. Number 5. Sine squared u plus blank is 1. Sine squared u plus blank is equal to 1. Cosine squared u. Number 6. Cosine of pi halves minus u is equal to blank. Okay. I don't know if this hint will be helpful or not. What is pi halves minus u? That's called the blank of u. Okay, yes. Sine u will be like, is the complement of u is pi halves minus u. So it's the complementary trig function of cosine, which is sine. Okay. Number 7. Cosecant of negative u is equal to blank. And all they're asking for is something about a plus or minus sign. Cosecant, yeah, negative cosecant u, because cosecant is an odd function. That's all they're looking for there. And secant of negative u is, nope, secant's an even function, is secant u. What's that? Cosine and secant. Yeah. Think graph. The cosine function, if this is the y-axis, going like this. So it's the same on either side. That makes the secant function the same on either side. So those two are even. All the rest of them, sine is opposite, tangent's opposite, cotangent's opposite, and cosecant is opposite. So all those are odd functions. Only secant and cosine are even. Okay. Now, your skills in application. Do any of the odds 9 through 49. That is a whole bunch of those. Do a few of those simple ones. Then get into some that are a little more complicated maybe. Do some that you might have to do a conjugate. Maybe some that you might have to change all the sines and cosines. Do some that have radicals in them, square roots, There's a whole bunch of things you can work on there. So go to any of the odds 9 through 49. Now, 51, I think when they first did these, they said explain the errors, but they didn't put red X's through them. And people didn't read the instructions and were trying to verify or solve something that wasn't true. They're saying, this is wrong. Find the error. That's why they put the X mark through them. They're wrong to begin with. So try to do 51. Don't get too bogged down on it, but try it. And by the way, all the odd number exercises have answers in the back. I don't know if that one does. It probably does. But they also have at calccheck.com, you can see, get tutorial help and worked out solutions for all the odd number exercises. So you can go there, and that's why I signed the odd numbers. So next, do any of the odds 53 through 57. Do either 59 or 61 or both. Do 65. Now you can certainly look at any of the exploration. They have 2 odd true false. You can work those 2 if you'd like. Don't expect to see any on the test like that, but it's still a pretty good thing to work through and make sure you understand why they're true or why they're false. There's 2 think about it. That's 71 and or 73. You can do those if you like. All right, any questions? 7.2. I mean 5.2, goodness gracious. Okay, the old gray cells aren't working too well today. All right, let's move on to 5.3. Oh, man. This has been one long week. For those who came in late, I have been having more car trouble, I think I told the early ones, I think I've ever had in a week in my life, okay? It's just been terrible. Okay. Right now my car is out of commission on Pep Boy's parking lot, and we're going to have to get a new car, I think. And so I'm in a rental car, and I've got to figure out a way to get it towed off of there, what to do with it, where to send it for salvage. It's a mess. My wife's helping a lot. She's doing a lot of stuff on the computer, but still a mess. Okay. Chapter 5, Analytic Trigonometry. 5.3 is solving trigonometric equations. And guess what? We'll use simplifying like we did in identities in order to solve. So we'll use standard algebraic techniques to solve trigonometric equations. What we'll do is solve for the trig functions, then solve for the variable. We'll solve trigonometric equations of the quadratic type. Okay? We'll solve trigonometric equations involving multiple angles. Okay? Come up with that. And we'll use inverse trigonometric functions to solve trigonometric equations. Okay? Usually when you get down to tangent theta is equal something other than the inverse of that will then be what theta is. Okay? That's usually what you're looking for, the unknown. So in the introduction, to solve a trigonometric equation, use the standard algebraic techniques, they just said that when possible, such as collecting like terms, factoring, whatever it is, just like we found before. Usually the best idea is you use algebraic techniques first and then get into trig identities next. Your preliminary goal in solving a trigonometric equation is to isolate not the variable, but a trigonometric function on one side and have everything else on the other. Then you use the inverse trigonometric function to isolate the variable. So for example, to solve this equation, 2 sine x is equal to 1. What would be your first step? Second? Divide by 2. Isolate the trig function. Divide by 2, you get sine x is equal to 1/2. And then you say, oh, I know some angles x whose sine would be 1/2, right? And that's where you go from there. They would be, by the way, what? So, angles x whose sine would be 1/2. See, we haven't left that behind. We're still going to drag that back along. Pi 6. Pi 6 is 1/2. Pi thirds is square root of 3 over 2. Remember, go up 0, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Those are your signs. So square root of 1 over 2, that would be pi 6. First little increment there. Okay, but not just pi 6. Pi 6 was 2 pi. 2n pi, because it's a periodic function. It's going to hit that. But that's not the only place. Sine is 1/2 in the first quadrant. It's also 1/2 again in the second quadrant. So that would be pi minus pi 6, so that would be pi 6 pi. Remember, use your reference angle there. Pi 6 would be the reference angle. Subtract that from pi, and you have pi 6 pi. So it would be pi 6 plus 2n pi, or pi 6 plus 2n pi. So you have a whole bunch of them. Infinite number, in fact. Okay, so to solve, this is what we just did. To solve for x, note in the figure below that the equation sine x equal 1/2 has solutions at x equal pi 6. You may not realize that, but that's what it is. This is pi, pi halves, pi quarters, pi 6 would be here, pi thirds would be here. So that's pi 6, and then pi 6 forward pi, which is 5 pi 6. And that's in the interval 0 to 2 pi, and then to get all of them, that would be adding 2n pi to this and 2n pi to that. Because you see, for every one you get here, you have one here, you have one here, you have one there, you have one there, and then for pi 6 pi, you have one there, you have one here, yeah, every 2n pi away. Okay, coterminal angles. We haven't left those either, have we? Okay, moreover, because sine x has a period of 2 pi, now they're getting to say it, there are infinitely many other solutions which can be written as pi 6 plus 2n pi, or 5 pi 6 plus 2n pi. Have to do them each separately because you don't run into any of those with the others. For n is any integer, positive or negative, or 0, you know. If n is 0, then you have the pi 6 and 5 pi 6. Okay. So that's your general solution. Two possibilities. So here's another way to illustrate this. The figure below illustrates another way to show that sine x equal 1/2 has infinitely many solutions. What we have here, or what I consider we have here, is a 2-circle, not a unit circle, but a 2-circle. So your hypotenuse is 2, okay? And at pi 6, your opposite side is always 1/2 your hypotenuse. So if it's there, it would also be here. And that was, again, just like what we were saying, use pi 6 as a reference angle, subtract that from pi, and that's how you get pi 6 pi. And then, one more array around, and you get another, and another, so 2n pi, or if you went backwards, 2n pi, or this one 2n pi, or backwards 2n pi. So that's where you get the plus 2n pi. Okay. Now, they say this, and it's perfectly fine. It's a legitimate thing to do. When solving, I guess I already said, any angles that are coterminal with pi 6 or 5 pi 6 will also be solutions to equations. And when solving trigonometric equations, you should write your answers using the exact values, like pi 6, rather than punching that in the calculator or doing an inverse thing and getting a decimal number. And that's always going to be an approximation. May be good to 9 decimal places, or depending on how many your calculator has, but it's still an approximation. Pi 6 is exact. Okay? Pi is an irrational number, so it goes on forever that pi 6 will be an exact solution to. If you have a computer that will do it, do it. It's no sweat. Okay. Can't think of anything else to say about that. Let's move to example 1. Don't think we're going to have time to do it, are we? So let's stop there, and we'll pick up with example 1 next time. We didn't quite get far enough to have any homework exercises, I don't think, in this section. But did everyone here get a copy of the second test? Okay. And you've got plenty of trigonometric identities to do from 5.2. So I would work on those, and then we'll do some examples in 5.3 next time. This is, I don't think, a very long, it is longer than I thought. Hopefully we'll get through 5.3 next time and move on to the 5.2. All right, good deal. Have a good weekend. Working on trig problems will make it good, won't it? Yes. Okay. We'll see you Tuesday.